Testando. E agora?
Fica apertando.
E agora? Sim, testando. Funcionou. Beleza. Só acho que são 10 quase 10h30, né? A gente vai pedir para vocês, estamos chegando aqui para frente, 10h26. Vocês podem ocupar as cadeiras, aqui tem um monte de cadeiras vagas. Isso, legal. Aqui também nas laterais, tá? Eu só vou lá no fundão, né? Aqui da cozinha. Lateral, cozinha, né?
Tem cadeira lá, empilhada.
Tem cadeiras ali do lado da porta, tá? Para quem precisar. Bem. Ótimo. Tem lugares aqui ainda, tá? Tem um monte de lugar aqui ainda. Pode ir chegando. Ótimo. Tá bem. A gente já começou a transmissão no YouTube, tá? YouTube, né? Se alguém quiser dar uma olhada ali como é que tá. Se funcionando o áudio, por exemplo, é interessante, é bom pra gente ter um feedback ao vivo aí, como está a transmissão. Bom, legal. Bem, eu acho que ainda vai chegar um pessoal, a gente vai começar às 10h30, tá? Certinho para o pessoal das aulas também, tá? Vamos esperar mais um minutinho. O professor Ângelo está aí. Professora Lindaura está lá. Daniel. Beleza. Conversei com alguns professores antes para o pessoal das turmas estão aí, né? Bacana. Esperar mais um minutinho para dar 10h30. O pessoal do YouTube chegar também, tá? Estamos fazendo a transmissão online. Está dando microfonia aqui. Mesmo assim, também está dando. Será? Deixa eu virar para cá. O pessoal sabe das coisas do som. Mas eu vou jogar para lá. Ele pega uma caixa. Tá bom. Tá bem. Bom, 10h30, né? Então a gente vai começar. Eu vou fazer primeiro um olá, né, em português. Daqui a pouco a gente faz a transição para o inglês, tá? Professor, então, Alex Wagner, né, da Universidade da Dakota do Norte, né? Está aqui para apresentar, então, uma palestra sobre o reticulado de Boltzmann, né? Então, desenvolvimento de escoamento multifásico, né? Dinâmica molecular e método reticulado de Boltzmann, tá? O professor, ontem, ele me fez um pedido do seguinte jeito: vocês fiquem à vontade para interromper a palestra e fazer perguntas, tá? À vontade mesmo, né? No meio da palestra, você pode levantar a mão e fazer pergunta. Você pode fazer a pergunta em português também, para que daí de algum modo a gente vai traduzir e ele pode responder, então, para vocês também as perguntas. Mas ele quer que seja alguma coisa didática, tá? E que vocês possam fazer perguntas, tá? Bom, esse é o ponto. A palestra, né, vai ser em inglês, tá? Eu vou fazer aqui uma breve introdução do professor Alex Wagner e aí ele vai começar. Professor Alexander Wagner is an associate professor in the Department of Physics at North Dakota State University since 2008. He obtained his PhD in theoretical physics from Oxford University in 1997. Following postdoctoral appointments at MIT and University of Edinburgh, he joined NDSU in 2002. Professor Wagner specializes in computational physics, focusing on Lattice Boltzmann method for simulating fluid dynamics. He is also an associate editor for Physical Review P, where he oversees submissions related to computational physics. Additionally, he serves on the committee for the Discrete Simulation of Fluid Dynamics Conference. Professor Wagner has made significant contributions to the field of Lattice Boltzmann methods, demonstrating their application beyond traditional Navier-Stokes systems, including fluctuating systems. He has authored and co-authored more than 50 papers on high-impact journals. So it's my pleasure to welcome Professor Alex Wagner.
Well, thank you very much for the kind invitation. I have no idea what you said in Portuguese, but I hope it was nothing very damaging. So, we have... Yeah. Okay. I know you are not physicists and you have a different backgrounds and you're not native English speakers. So please do, ask lots of questions and feel free to interrupt me at any time as I'm talking about things here. As Luiz just said, I've been working on Lattice Boltzmann methods since my PhD. And I was just lucky that Lattice Boltzmann methods, there was actually lots of methods at the time that were popular. There was like DPT, there was stochastic rotation dynamics, there was a large number of possible sort of discrete fields that came up. That this all originated from lattice gas methods, and for reasons that have nothing to do with me, somehow Lattice Boltzmann became a very popular method, which is why people like yourself know about it now, or have heard about it now, in completely different fields. And I've been sort of involved in the development at different stages. And so what I'll be talking about today, yeah, that works. Yeah. So, I want to just take you back to the very basics, right? So, if some of you aren't even involved in the simulation of fluid dynamics, but if you were as an engineering level, you always think about the Navier-Stokes equation as the problem you have to solve. What I'm trying to convince you of today is that that's not actually the reality. That in fact, in reality, the reality is something different. In fact, you have different ways you can describe this reality. And these different models, of course, have to be...
We can turn this mic off.
Okay, sounds good. Yeah. So, perfect. So then we have this physical reality that's something separate from the models that we build to describe this physical reality. And if you do that, then you want to have these various descriptions to be consistent with each other, right? And that turns out to be surprisingly non-trivial. And I would argue it's not been fully solved. And what I'm talking about today is like a work in progress, trying to match different methods of simulating the same system and trying to understand a little better about what really the physical reality is of what we want to describe. Okay. So let's look at a real example. So this is, up where I live, there's a lot of snow. And so this is last spring or maybe spring a couple of years ago, I don't remember now. So we see here this river flowing, and you've all seen things like this before, but if you look at it, well, what do you see here, right? You see water, you see the liquid-gas interface, right? You see a solid, which happens to be the solid that corresponds to this liquid, right? So this is some ice. That ice is in some kind of consistence, so depending on the temperature, the ice will grow, it will shrink, right? You'll get melting or freezing, and all this stuff is going on here. But of course, the reality of what's happening there is none of these particular things that I just said, because those are just models that we have in our mind. So, as an engineer, you think, oh, this is free surface flow, I need to solve the Navier-Stokes equation, I need to solve some kind of boundary problem, and then maybe you have to look at entrainment of bubbles, and you've seen these problems before, and you know in principle how you would go about it. But that's not a Navier-Stokes equation, right? That's an actual real system, and this reality may well be described by the Navier-Stokes equation for certain aspects, but that's not what it is, fundamentally. And I think sometimes it's useful to step back to kind of just realize that the models that we have really are not the reality. The reality is something completely different. And the reality is something that we can really describe on very different levels, leading to models that can look vastly different. So one way of going about it is to use these macroscopic equations, the ones that you're probably most familiar with, like a continuity equation, Navier-Stokes equation, heat equation, something like this. But you know that in principle, matter is discrete, right? So it's made up of atoms. So you should also be able to describe it as the motion of atoms directly, right? And if you've looked a little bit more into the physics of things, you realize that the classical motion of atoms also is not the reality. You know they're quantum phenomena. And so you can have a quantum mechanical description which looks entirely different again. And we don't know if that's the end of it, right? If that's actually a description or not. But since you have all these large variety of models, they should all give us the same predictions for the reality that we can see. Right? So we see something happening there in this picture before. And any of the models that we have should give us something that is consistent with our observations, right? And so this is, of course, also a message that I mentioned. This is the connection between the microscopic and the macroscopic, right? And surprisingly, there is no universal way of actually deriving Navier-Stokes equation for multifascic flow from macroscopic molecular description. Right? Only because we have sources by the kinetic theory, where you describe a rarefied gas with gas energy by this quantum equation, and we'll actually go through very briefly what the theory behind that is, and some of those equations are following, but I'd like you to at least know what's going to be involved in this. And typically what happens is that in the development of these methods, people either say, well, I want to do a model that fits within our Navier-Stokes equation in the way that I think is right. And then you can see, well, if I add these terms to fudge things, will I get what I expect to get? That's sort of the top-down true is that example that was presented, which would kind of cut out the middleman and arrive at a new description, which is sort of fundamental to the way that you can map it directly to an underlying physics. So, in the macroscopic view, it looks like this fluid that you're looking at there is something continuous, right? So we have continuous amount of water that can displace, so it's described by some kind of density field. It'll have some momentum associated with some kind of flow field associated with it. And then we can ask ourselves, how do these fields evolve? And the answer is not actually that obvious. It's driven by conservation laws. And in this macroscopic view, we have three conserved quantities, which is mass, momentum, and energy. And really, these equations are, the continuity equation is an equation for mass conservation, the Navier-Stokes equation is an equation for momentum conservation, and then the heat equation is an equation for energy conservation. And we don't really know fundamentally why it's exactly those three quantities that are conserved. We know it's not entirely fundamental because in relativity we know that mass and energy are actually transferable. You know E equals mc squared, so you can actually transfer mass into energy directly. So they're not separately conserved. It's one thing. In principle, there could be more or fewer conservation laws, but that's just the world that you happen to be living in, right? So, if these quantities are locally conserved, we arrive at basically saying that the change, so mass is given by the divergence of the flux of the mass. So, mass can only be changed by moving out. Now, in principle, there are more things that could be there, higher order moments of things, but those are not conserved, which means that they can get to equilibrium state very quickly. But the conserved ones are different, in that they cannot be brought to an equilibrium state locally. They can only get to an equilibrium by moving, and moving is more tricky than changing things locally. That's the reason, the underlying reason, why this tends to be an easy way of describing the continuum mechanics of fluids. Now, so this quantity J is the current momentum. This momentum flux tensor is essentially the flux of momentum alpha in the beta direction. And then we have the heat flow quantity Q alpha here, which is the flux of energy in that system. And this, if things are in fact locally conserved, would be the correct description of high energy, except of course we expected this in terms of the new quantities I and Q, which is not much use because we don't know what they are. Right. And so we get the momentum flux tensor, and we get this deflux tensor, which is two new quantities. And you can only solve them if you're able to express it in terms of quantities that you already know. Typically what happens is it does stick with mass, momentum, and energy. The stress tensor is expressed in terms of mass, momentum, and energy, and the heat flux is also expressed in terms of your mass, momentum, and energy. Now that's not fundamental, but that's the idea how you arrive at something that you can solve the stress tensor. And it's actually subtle because things like molecular dynamics don't quite do this, because in molecular dynamics you have particles that interact via force. And if your particle projecting via force, they transfer momentum, non-locally. And this goes back to a really key question, which is that do you actually get interaction at a distance, right? So this is part of already human, right? When we kind of the fluid dissolves the motion of planets. How can an object in this distance away act on another object in distance away, right? And in fact, we don't think about it this way anymore. We don't believe that that's true. We believe that it takes a finite amount of time to transfer information kind of nasty, but it's the simplest thing you can do to say that if you have two bits of fluid moving with different velocities, there should be friction between them, right? So there'll be force that slows them down. So that's the viscous, this is the viscous stresses, and this is the sort of the compressed, and there's also some viscous effects of that. And similar to the heat flux, the easiest thing is, well, energy gets affected by the flow. You have the divergence of this stress, and so basically, as if you have friction, that friction goes and generates heat. And if you have bits that are different temperatures, you get a heat flow, which just has the heat diffusion. Right? If you put something warm, you put something cold, you get a heat flux in the direction of that gradient. And so those are the simplest constituent equations you can do. And with that, we arrive at our hydrodynamic equations. Right? And you can extend that to more complex phenomena. You can put in different forms of reactions. But this is a very good description from many publications. Right? That's what 99% of engineering does. Solve these particular equations for the hydrodynamic properties. So, and sometimes you add additional stuff in there, like boundary conditions or chemical reactions or multi-phase effects. I'm not going to go into details of all of that, but this is just a description of the way this continuum evolves in terms of your mass, your momentum, and your energy. Right? You have the field for each of those, and now they evolve according to this differential equation. It's essentially just continuity equations for these material quantities. And the corresponding utility equation. Okay. Now, oh yeah. Now, because as a check, you know that that's not the only way, right? So, since the time of this, you have suspected that nature might actually be made up of discrete things. Interestingly, so while you may have heard this in your high school classes, that really wasn't accepted universally until the early 20th century. There were adherents of this idea when in Greek philosophy under the name of Epicureans in ancient Rome. There's this very, so the Romans are known for their engineering, not really for their science. And but there was one guy who wrote this interesting science poem called De Rerum Naturalis, about the nature of things. And if you get a chance, it's by Lucretius. I highly recommend reading it. It's prophetically correct in many ways about how we think about microscopic things. It's also spectacularly wrong in many other aspects of things. It seems really bizarre that you would think about things like vision or so, that describe in this way that seems really strange to me. But it's very interesting to just see how our thinking has evolved over time. Right? There were people like Newton who were very partial to the idea of these particles, but it really was not accepted. Now, in 1905, Einstein had this interesting paper that described Brownian motion, which you may know about the random motion of particles around the origin of life. Noticed that pollen was actually moving. So, oh, this must be the origin of life. But then he was actually a good scientist, and so he did the same thing with dust. Dust does exactly the same thing. So it had nothing to do with pollen being something living, but it actually had to do with this being a small particle suspended in water. And since he had access to the microscope, he could observe it. So the first time he could observe suspended motion. But it wasn't really understood until Einstein said you can understand this in terms of the direct collisions between the dust particles and the discrete water molecules. And because he could quantitatively describe them, we describe how they depend on the temperature, see that exactly works. That's really what settled the debate of whether nature actually is continuous or discrete. And it's not that long ago, right? It's a little over 100 years, which in the grand scheme of science is nothing, right? Now, And you have this probability distribution from itself. It tells you about where the particles are. It tells you about the probability of finding the measure. And it used to be like obscure subjects a little bit, which not too many applications, but it's really coming to the forefront. Also, the computational version of quantum computation, where quantum computers are really interesting to what they can do because they do not obey the typical law of physics that we are sort of know and love, the classical ones. They behave very differently. It allows them to do amazing things very fast, but in their own really strange limitations. And so, there's a lot of effort going right now making use of the quantum mechanical world to do computation. Okay. And so this describes the fluid mechanics part of the differential equation. Now of this wave function. And that should be another perfectly good description of what our fluid is. And, so in between wave fluids, you say, well, you can actually treat these particles as classical, the point particles interacting with instantaneously with pair forces. Right? This is what goes under the name of molecular dynamics, which you may have heard of. And you just model each and every discrete particle that you deal with, their forces that interact with them, and you can describe their motion that way. Right? All this solves is, and this should work very familiar to you, I hope, because that's the Newton's second law. Right? Saying that the acceleration of the particle is given by the force acting on the particle divided by the mass. And so now we've reduced what are these more or less complex partial differentiation for our secretive quantities to just this. Now it's why it cannot be the equivalent solve that we solve that for another particle. Here we solve it for all the particles. But practically this is really simple. Right? Very simple, much simpler than the particle equation. And somehow this should be the same as these aerodynamic equations. Right? So how do you get from one to the other? It's also obvious how we do this, and took it on we have these very different models, and every one of those should describe the same thing. So there have to be some equivalent ways of getting the same thing. And we know they describe different things as well. So they're not entirely equivalent, they're not one mapping. But you should certainly get the microscopic models mapping onto the more microscopic models within the macroscopic range, they should give the same solution. And you should be able to derive the more macroscopic model from the microscopic model. And you have different niches where they could be applicable. Now, microscopic models, there's no limit to how big things can get. There's only limits to how small you can look down. And then you have this quantum description, you get probability of finding particles at certain positions. In principle, goes for all lengths of time scale, but practically it's hard to solve it for more than 10 particles, say, just because it's a really tricky problem. And you can make approximations to get it into more, but to really describe it mechanically, it's a bit complex, right? But conceptually, there's no difference. Conceptually, you can definitely describe the universe mechanically. Nobody has done this, or with special hope. But it seems like it should be the same, right? That's the description of the particle. Now we can look at bigger, much bigger, right? So we can look at like maybe a million particles, so 10 to 6 particles, and we can look at it for small fractions of a second, maybe tiny fractions of a second. And you're looking at small, very small descriptions. Now, you that's still hydrodynamic systems because you're looking at macroscopic systems, right? You're looking at planes, trains, automobiles, big stuff, right? Oil wells. But these other limits involved, they're practical restrictions, they're not fundamental. So the expected results in my model needs to be this macroscopic models, which in practice means we should be able to derive the evolution equations for our macroscopic systems from the microscopic equation. So you're not going to already got deriving limit equations from quantum equations from the PN factor that starting with the net equation y. We're going to worry today about going from the classical equation to the more macroscopic equation. And the way this is done, there's a lot of this historical stuff that is the way people have been thinking about it. They go to something that's known as the Hegel equation. And this is just the when you construct the Hegel equation, you have by hierarchy and you write it also a description there. This is where the most description comes from. And the reason I'm telling you this is that often people think of the Boltzmann equation as the more fundamental multiple equation, but really there's a lot of stuff you throw away in the Boltzmann equation. You're losing a lot of things that you may not be fully aware of that people throw away. Right? And then you go to the Boltzmann equation to the Navier-Stokes equation, which if you've been working in the field like Boltzmann, you've probably done yourself. Okay. Very briefly to this. So the basic idea of the Hegel equation is that instead of in principle, but in reality you have particles sitting in a problem at a point, and they fall to limit equations. Instead of looking at one particle, now you look at a whole ensemble of particles, because your argument goes like, I can't really measure where all my particles are and what their velocities are. I can tell you roughly what the mean density, the mean number of particles in a certain area. So I really have only like some kind of ensemble of all these points that make my problem much more difficult, so to speak. Instead of having just one specific system that I involve, now we're looking at the evolution of the whole ensemble of particles, of systems of different positions that macroscopic detect. And basically what this tells you is that change of this density is given by the flow of particles moving along the VI in a certain direction, and then the momentum of the particle being changed by the force. That's basically just put in your equation again to arrive at this what's now a continuity equation for this real density of state in and so we're not talking about the one real system, we talk about many systems that all kind of look the same and that behave properly. Okay? And why we do this? Because now we move from something that's actually discrete to something that's actually continuous. Right? Because our description, of course, is a continuous description in other dynamics. Now, what exactly this everything is actually something suspect. That's what we do now. Let's say, many people know this, you take the flow of fluid around the cylinder, right? And you start up this flow. And you know that there's the stability development from common three, right? So you hold from common three. And so basically what happens is you probably, if you take a stick, right? You go to the river or to the ocean, you take a stick, pull it to the water, right? What happens is that if you do it really slowly, you just move the stick to the water. And if you move it a little faster, you can find all the eddies behind it. Right? If you do it very fast, train bubbles, cleaning out. So there is a shape that you move just a little bit, you can see the eddies coming. You can see it through your bar stacking up the bright light, and you can actually see these eddies forming. But what's interesting about that is that exactly when these things form is kind of random, right? So if if you average over all information of eddies, there's eddies happen at a different time. And once you study everything, there's no more eddies. Right? So actually something really weird is happening. That's not really what you're looking for, and that's something now that I'm going to run into in a little bit. That's something to keep in your mind, that there is something actually fundamentally fishy about this. Okay. Now, again, we don't look at details, we have a description of all these particles, right? But you can write it in terms of the evolution of fewer particles, right? You try this, you integrate over all the particles you don't care about, just the particles. So you can S particle distribution pattern, and you can write on the evolution equation of the S particle distribution pattern. But keep it in mind that it actually depends on the S plus 1 particle distribution, because you can interact this particle interact with one more particle, but you can go about more particles in there. And you get this big evolution equation of this S plus 1's distribution function. This is not going to be integrated by hierarchy. Don't have to worry about it, except in one case, because if you're at the very lowest level, there's one particle distribution function, probability of finding particles with respect of dB, and the evolution of that is given by the two particle distribution function, integral over two particle distribution function. And now, if you say the probability of this, what does it mean? It's the probability of finding the particle at position x with a velocity v, and a particle at position x2 with another velocity. Right? And the assumption that you make that that's really just the product of finding a particle here with its velocity and the particle there with another velocity. That's very wrong, right? Because you know that they'll have interacted. They should, in principle, and in most cases, be correlated, right? So what this particle does and what the negative particle, it will know what this particle. Right? And there'll be some relation of how they behave respective to each other. But you make a very simple assumption that you can forget about that, proved by the name of the molecular chaos assumption. And they don't really know about each other after all, and everything you can forget it. If you do that, we write as possible equation. Now, because it's thrown away so much, you suddenly. So this equation would exact. The possible equation is everything but exact. And it can only describe the loose ideal gases. Right? The equation of state suddenly has become, so this one has any equation of state that you want, depending on this will be described. Once you've applied the Boltzmann factorization approximation, you throw away most of it. And you get an ideal gas equation of state. You can actually show that once you factorize it, there is this functional. It's the H functional, which gets minimized. I tell you about this because if you ever model system climate topic, you know that there's another equation you like to concern yourself with, which is the entropy. Right? And you can actually put the entropy something that being vicious. And it's a weird equation, respected also, because it's not reversible in time. So if you have entropy at one time, you have an entropy another time, you can tell which one happened first, which one happened last. Right? That's not true for Newton's equation. Newton's equation are completely reversible. Newton's equation don't know. If you take in the system, you turn the velocity in the opposite direction, it will move back in time exactly. So Newtonian equations don't know what entropy is. But here's finally, you get this second law of thermodynamics out of this Boltzmann equation for very dubious reasons. Right? Because they made a mistake by assuming that they can factorize this. And this is a funny thing to derive this, right? But suddenly you get the second law of thermodynamics, which is not a bad thing because we know in our real observation that's something that we find here. It's one of these funny properties of the Boltzmann equation of factorization. And suddenly we get highly irreversibility. We also get out of this by minimizing this. This is minimized exactly by what you hopefully all know special velocity. The normal distribution of velocity around some mean velocity u. Right? If it's 6, then temperature is very small, the distribution is very large distribution company. So that all comes out of the most motivation. But we've thrown a lot of stuff away in order to get it. And then we have to mostly get this complex collision operator that we have in the last one. But what it does is it brings you close to equilibrium. This equilibrium that you just go down. And you can simplify your equilibrium by saying, well, instead of describing exactly what the collision does in this table, we actually some relation like top for the equilibrium distribution. That's very roughly what the equilibrium looks. This now gives us limitation and collision. And we can define in the field that we cared about very much when we had our macroscopic description, but other description, we find the density of the individual structure F, this is the velocity, like the velocity, which is one of the rho times the integral of the F distribution function times the velocity, and you arrive at some kind of temperature description, which is like thermal energy, by D minus U squared. One half there, but details times the F. That gives us this effective temperature that you get at this point. And so this is how the macroscopic fields. And we can ask ourselves, how do they evolve? If things evolve according to the Boltzmann equation. And indeed, what we find is that we can approximate now an F function with the F equation in terms of F0 and derivatives. This is sort of the big trick, because we don't know what the F's are, right? But we know that the F0, the equilibrium distribution, depends on the row figure on global removation, right? So having a differential equation in F is no good, but having a differential equation in F0 suddenly means that we have a differential equation in terms of our conserved fields. And so if you write F in terms of F0 and derivatives, and normally you're not to do this, you can insert an equation to itself, which typically gives you just, constants. But in this case, because you insert this equation back into the F that is in here, you've inserted them at a different point and actually gives you something unique. You get a whole expansion of this in higher order terms, and you can write down an evolution equation that now contains F0s, 0s, in higher order terms. Here. And now we can sum this equation over conserved quantity. And because conditions preserve mass and energy. Exactly, this term will always be 0. And then we set that with this dimension equation. We have that term. We will write exactly what we're looking for. The macroscopic equations only for linear. So that's what I was going to do. When we threw away all the correlations, suddenly we're left with stuff like linear. Apart from that, and if you want to, you can have an internal form term there as well, which is the equation, and you arrive at a model that now has derived the hydrodynamic equation just in terms of the Newtonian physics. Right? This is the way you go about it. Very brief. And this is really useful because we want to, of course, describe these systems that I showed you, like water flowing, the oil well bubbling, whatever. And the question is how do I want to describe it? Right? And traditionally, people involved in the macroscopic problem, I should take an Navier-Stokes equation, just derive them, which goes by the dynamic. And it's really the volume of proof to the volume of engineering since the 50s of the 80s. And this equivalent level of the difference in the molecular development is that we can also use different models to describe the same kind of fluid phenomenon. And one way to use this is to use molecular dynamics. And there you actually just write down particle positions, particle properties. We've also been going to phase, right? They change the position of the particle with the velocity, and the velocity with the force of the spider. You use some kind of approximate second order or higher order method to do this. Now, this is actually really nice message in the way that a lot of the stuff that will struggle to do with methods for models comes for free, right? So you want to look at some multiplication, it's there, right? You want to look at liquid coexistence, it's there. Liquid gas coexistence, it just emerges out of it. Here's an example from the occasion, which is called this semester. What we wrote this quick little MD code, which really just nothing fancy, just solve the integration. And here we have an example of some 7,000 particles. I made them two species slightly different, and so they all attract each other, but the blue and green ones don't attract each other quite as much as the blue ones among themselves, and green ones among themselves. And what we get here is two liquids, and then you have a gas. The gas itself has the structure, so you see it's not a single particle that are moving around, but it's dust that are moving around, so you gas consistent dust. You get all the structure out of the MD with basically no experiment. Let's hope you get and as long as you have a good model, so how do you think you can model very different substances as they run into each other, right? You also get fluctuating behavior. We know that we call it the principle of fluctuate. Let's come out with trees. This model just starts model, you put it down in the trees, you get an equipment feeding position. The model is a very funny 2D feeding transition. But it's all that principle. Now you can do it in 3D, get a little more fancy because having another dimension means that instead of having at least, I don't know, there's some partners equivalent in 3D, which becomes more expensive, but it's still doable. I think we have parallel, the non-parallel version, you know, that CPU, so you can use IDS. So the evolution equation is exactly the same, it's just the fourth law. But the way the phase is formed, particularly the solid phase, is quite different, right? Because 2D, you have hexagonal structure, right? But in 3D, they have a lot more neighbors, right? So they act more strongly. Also, if you want to rip this, you only have to have one line. When 3D, you have a whole, you have many more ones, it's much harder to rip something out. So they behave quite different. So the education process and the routing process look different here than in 3D. But that is just the problem of this issue of geometry. It's nothing to do with the fundamental equation approach. It's just that they can arrange more closely in 3D than they can in 2D. Now, this is the whole thing that Boltzmann world started. You can, so the MD is great, but it tends to be limited to how many particles you use. And the idea is to use something that's known as a lattice gap. So instead of particles being able to move anywhere in space, they can only sit on that position. If they move to neighboring lattice sites, space by some kind of lattice will isolate the ideal T is an NDSU. What we do that position. And you just move them about to neighboring sites, right? In such a way that so you move them and this thickness that you rearrange them. So you move them about in such a way that you observe you overall mass, so you don't add or take away any particles, and you don't change the momentum that means the total momentum of particles is negative. That becomes a really simple form. Right? In fact, so simple that as engineers, they probably would laugh at that, well, that's kind of funny, but really useful. Right? Because obviously it's so simple, it can't track anything here. And let's look here at the one-dimensional version of this. And in fact, it looks kind of rough. All you do, so we have a particle, there's three options. Its neighbor is moves to the right, or we move to the left. Right. And then what happens is you have all the particles doing their steps, moving in a certain direction. Then there are new sites, they equal among themselves, but only in such a way that you have the same number of particles, and they can't change their overall dimension. And then they can and then just repeat this process. Right? So it's absolutely nothing to do. Right? It's trivially simple. And you would think, well, clearly this can't give you anything useful because it's such a trivial thing to do. Right? And in fact, what the conditional operator can do, it's embarrassingly trivial. You can have particles move from this side and particles move from this side, right? So both of them moving in. They can become rest particles of water and stay there, or two particles that are standing here and push each other away and start moving. That's it. That's all they can possibly do. That's the only operation that will both are in momentum. Okay, so something trivial like this. What can it do? So what you have now is you have to look at probabilities. So you look at probabilities that two particles are standing in them, they're both non-moving. What's the probability of them starting to move? What's the probability of two moving particles that meet each other to stay still? And you say that, well, you get sort of the way that you want to predict is if you have two moving particles that meet each other, they just stay and stand. Two moving particles will only get moving with the probability of 1x. Right? And that's your model. That fully describes what this model can do. Right? So you have particles on the lattice, they move according to the velocity associated with them. Then they rearrange moving particles that meet and become stationary particles that meet and start to move, but with a lower probability. Many of them just decide not to do anything. And that's all it does. So it's a very simplistic, utterly trivial model, very easy to implement. Okay. And you can ask yourself, well, what does it actually look like? On average, if I have some local velocity, mean local velocity u, and I have some overall number of particles n, and you can actually analytically solve this. You can show that this is the equilibrium distribution that you get, so that's how many particles on average you can find at velocities I, given that I have some density n and a momentum j on average. And you actually find the calculation for the probability distribution of that, not just the expectation of the that turns out to be a total distribution which is made up of statistics for all. And look at the setting all of statistics. The total distribution where the NI limit is the expectation value and the NI is the integer value. That's the probability of having exactly NI particle at the site. And you can find a local equilibrium distribution, which, even though depends on any day, locally independent of these. Okay. Now, you can do this, and you actually find that this is competitive with the smaller methods. Not much. And you can ask yourself now, how does this really behave on average? And that's where you get into that fourth method. So you define this Fi to be just the expectation value of this. So you want to think about you're running this calculation not at once, but many times. Since you have random outcomes, you get many different possible outcomes. You average over all of them. And now you get an average quantity Fi, and you get the evolutionary gradient with Fi. And you have the new quantity which operator omega I. Now, this looks exactly like the gas space class. But that's just the fact. It's very, very different animals because the gas was discrete and the conditional operator was the random operator. Whereas this Fi actually continues quantity. And this omega becomes the deterministic conditional operator. So it's distribution of the average impact. Okay. And you can look at what this conditional variable looks like just by averaging over the probability of finding the NI times the operation for the NI again. You take average over that, and that will give you this the reservoir conditional operation. And if the NI are not consistently independent, just go back and try whether or not that case is another. Okay. Now, you would want this conditional operation to be just dependent on the NI, whether or not that true is it's usually approximately true. It's true is not exactly true. It's approximately true. And the question is, well, if I describe it in terms of a just now let's apply this very simple boring model, both in the ballpark version and in the Navier version to a not so boring model, which is a shock factor. Okay. So what we do is we make the assumption that this polynomial is actually given by this BTK like division operator, right? Which means with this property, which I did show you for the thermodynamic extension stuff, now, so that is also when you can actually get something good to go about that later. So the omega is political probability of target colliding. If this becomes larger than 1, so that the omega between 1 and 2, we get this polarization, which is a very low probability. Okay. Now let's put the next one. Here's the example of this operation. You just said, so you set up two densities at a different point, then you get them flow. And so I'm going to show it to an expert shockwave. You realize this looks a little different than what we used to because this is actually isothermal shockwave. We don't have separate energy based at this point. And you can see that that essentially agree with each other. We get exactly the same result. And there's an analytic solution of the order equation, and apart from the fact that this thing could be sharp here and this. So this is actually pretty good, but this one would be sharp. So because there's the software to be a bit spread out a little bit, but other than that, this gives you exactly the result. You can show in this curve a wide range of parameters. And here you can see what the division operator actually does. The division operator only acts here and here, essentially, and you find that here your operator operates in the opposite direction from here. There's an addition but for that gas is also living the same way. Here we have the gas model, and in that model, when it's not about the behavior that would affect that. And you arrive, of course, here at the macroequation that you talk about, and this is exactly the usual gas. I'm not showing you how to do this here. But it's been shown that these disposal methods are actually at least compatible in terms of speed and performance to standard PFP methods for many applications. Okay. Now, this is how people have divided in principle. Now, here's a completely different way to do this. If we want to know how these particles should move, again, find this gas that is complement directly from the way we do this is again, this is so the way you do this really is kind of true. You have your MD particles, they do whatever they're doing in space. And if you look at the green bit, that's all the particles in it. So you apply this red set of boxes on top of your simulation. Right? It's some particles will be in some boxes, other particles will be in other boxes. The green particles here are the particles in the middle box. And then as they evolve, they move through these big box, right? and many of them will stay where they were, and some will move to neighboring websites. Right? And all we do now is to interpret these three particles as particles that are moved from this data site to that data site. Now we have this gas grid, which is a blue grid. The particles sit on here, and depending on where they move, they determine that they're ice moving into these neighboring data sites. If you wait much longer, you need more arrows. You will put all the arrows there, right? But if you do it for a relatively short time, they'll stay where they are or move a little. Right? And you can use it to find the NI. And since these NIs are moving, so you know the NIs at any one time because you can measure them. Right? And now you can ask yourself, what does this? So you can define a collision operator from the NI. The NI you can fundamentally know the particles. So the NI are the particles that are now at this site it came from this NI space that site. And then they get rearranged, right? Because they may move somewhere else. Right now. This operator can't get the top of the red gas. Except that now the collision operator doesn't necessarily obey any particular rules we want it to obey, but it comes out of whatever molecular dynamics tells me that. So this lattice gas that we now have here, we know that exactly the right thing that it was on the lattice scale that we have imposed, right? Because it's just the cross grading of the mapping of the molecular dynamic results onto the lattice gas. Right? In some sense, this is the fundamental way of deriving the lattice gas. It has to do the right thing. Right? And now the question is, well, can we actually understand what like it does this? If I take this lattice gas, do I get something that looks at all like the Lattice Boltzmann that we used to, or does it do something between the edges? And the easy thing, so let's do this is an example of what we do. So I just it's an anti-simulation of relative dense particles. They evolve according to fusion law. And then painted the particle middle red, right? As before, these particles will spread out, right? And depending on the time that you use them, you can move to the middle, or the more. And here now, one of the main left side. The longer you wait, the more they'll disperse along this line. But it should be very simple to understand what these NIs are, right? Just impose the lattice and you just go for particles. That's all there is. There's no magic. Right? Okay. Now we can ask that what is the probability of finding particles in a certain distance? And the easiest assumption you can make, and you know that if you look at very, very short times, right, they move with their velocity, right? We know that it's Gaussian distributed because of this measure of Gaussian distribution. You also kind of know that very late time they distribute around, so it's going to be Gaussian distribution. So the example was probably at least well approximated by Gaussian distribution for all times, where you measure the mean displacement here, and you displacement is just probability for displacement is just given by the Gaussian distribution. Okay. So, and then you calculate the equilibrium distribution and the application volume of the NI, which is the probability of finding these particles with a displacement over these delta function basis set, is it at site NI or was it at site EI and X and minus delta. And that you can integrate, right? Analytically, which is beautiful. And this, so the comparison, this is what we can normally use to learn also equilibrium distribution. This is what you get out of these just solving the distribution. Hence, because this one depends on this A quantity, which is basically that initial statement of the lattice spacing. So if I look at very short, time period, it will move very little. So all particles will be red particles, right? If I run this very long, basically, then they spread out equally over all the neighboring sites, right? But somewhere in between, are these funny, so here we have this WI value, which is what we want to do. And these particular values, the John here has like red and dotted line. Turns out that there's exactly one value of the concentration H-band 1.6. So that is being very well. So in this very special range, suddenly we recover what people assumed before from fundamental molecular dynamics, just looking at the living. The one particular value of H there is very conventional. And now, of course, this is only a unit. So now, when we change our velocity, we can, of course, control the velocity in this relation, right? It's basically the practice with the velocity. And we can see what this looks like. And this is what this looks like. So we look here at how these different velocities are red particles. This is the coming in the direction of the flow. And this is going to the opposite direction. And this is going to the diagonal ones in the direction opposite. And we have the solid line, which is the center dimensional. And we have this one. And you see it actually has some line properties that essentially agree up to velocity of 4.1. But here there's different, of course, it's not really anything. It has to be this way. They have to, so basically, the red particle in the particle group effect has to stay that one. Right? That's why the symmetry of the empty system, right? If I move this, which involves half of that is facing the shiny red above the red particle and the moving particle there have to change that. And we'll go up and then we'll go down. So yes, we're covering essentially the same equilibrium distribution in the range that we expected. Right? And so if you look at that also curve, this is very current. We're getting very close to what we've done already, but now we're not doing it randomly, but we're deriving it from an underlying equation. Now, the reason is because it was the people assumed that the densities are for solid distributions divided by gases, and that the probability to the I are all for solid distributions around the
Fala, meu querido.
and we can detect it.
E aí, professor, uma experiência de 6 meses, passou por formato. E tem uma campo que se botar energia. Mas energia, mas não era energia. Era esse professor, 6 meses. Queria ver se qual foi o problema, né? Esse negócio de espírito. Eu queria ver até que nível que estava usando e quanto tempo usava, ou se estava interparado. Cada tempo tu faz o coração. Faz o coração. Ele dá mais alto. Então de parede. Tipo assim, de parede. Tô fazendo uma transmissão ao vivo aqui. Depois tem que botar isso aí na tomada. Queria ver como é que eles usaram, porque é a mesma, tá vendo? Era uma naquela grande lá. Eu só queria ver como é que eles usaram. Agora o nível deles. Porque essa máquina aí, eu tô achando que a gente deu azar, cara, porque a gente parece que ela é boa, mas a minha ali, eu sempre deu problema. Mas ela não botou de fácil. Esse é técnico?
Eu bato doente?
Tipo o quê?
Falou com a cidade.
Esse é bom.
Tá, eu acho que vai gostar mais de conversar.
Talvez tenha mais ligação. Mandasse pra mim?
Eu vou ver.
Aqui o pessoal da menina da terceirizada aqui. No auxílio digitar, cara, eu percebi que quando eu digito, aparece no vídeo. Cara, muito ruim o microfone. Esse microfone aqui não deu o original do lapela. Não, aquele microfone pra capturar que eu nunca usava, né? Aquele outro, mas esse microfone é ruim, cara. Tá baixo pra caralho. Faz transmissão. Não dá, cara. Aquele outro lá que a gente tava usando, parece que deu problema. Mas deram uma batidinha, deve ser alguma coisa de contato. Vou chamar a memória aqui, porque daqui a pouco tem que pegar os vídeos. Eu trouxe uma cara. Que é esse cara aqui?
Basically, the model says that particles in the same cell like to move in the same direction because they interact with each other. If you do that, next slide, you can have a model that, next one here.
Boa tarde, Convite, tudo bem? Eu sou estágio obrigatório de voluntário. Eu gostaria de saber o responsável pela unidade concedente. Nesse caso é o Udesc, né? Só que eu coloco os dados do Navier ou do Hegele indicado. Do diretor-geral ou do diretor ou do reitor. Essa dúvida. Aí eu quero preencher certinho para ser aprovado ali no sistema.
Esse é do Emil.
Now, to do that, we're all talking about deliveries. We like to do this with dynamic systems. So we need to understand what the traditional operation is like. And there is some industry very much with the shift rules, but I'm already late, so I won't talk about that. But I'll briefly mention that this is something we actually apply to interaction systems that follow when we look at so let's look at this example here. This is what we looked at before. We have droplets, they face separation. Now we can cross-grade this and get some kind of average density.
Cara, eu acho que a galera não tá nem entendendo. Ele não é americano, o inglês dele é duro, cara, ele fala rápido. E extremamente específico, acho que é o mesmo. Eu acho que 70% não tá nem compreendendo o que tá dizendo.
So you can ask yourself, in what sense can I use Boltzmann limit on this system? Right? And if you actually look at averaging
Eu não quero que eles peguem esse hábito, cara, de
over all possible cases,
esse comunicação, mas
because it's
só que tu tens um cacuetezinho um pouco extra. Tu tens que mexer com o equipamento, tem que mexer com o ODS, para transmissão.
if you average over all the dimensions that you get, we don't have a droplet anymore. It's all spread out, the droplet's gone. So that's not exactly what we mean by the Boltzmann average. One thing that the question of what does it actually mean? In fact, this has been argued before this draft demanding it. He said, well, what do we actually mean? What do we average over? We don't have ensembles. We only have one real system. So talking about this density in the real equation of initial state doesn't make any sense. We have one system. This one system doesn't have one
Não consegue parar a transmissão no YouTube. Ó, tá transmitindo. Você diz que encerrar. E ele vai perguntar se tu queres fazer alguma edição. Diz que não. Aí dá ok, vai dando os ok. Aí depois ele já vai pro YouTube automático.
Sim, ele dá o upload lá. Beleza.
Ele vai meio que automático.
Só encerrar. Se encerrar no caso aí, acaba o que? Meu dia ali, no caso, meu dia 10, meu dia.
Não sei, cara. Preciso pegar meus filhos. Tem que chegar às 3 meio-dia lá.
Vamos falar então. Vai ficar aqui. Eu só preciso de um toquezinho pra fazer uma transmissão. Não sei qual horário que vai ter. Mas eu fico aqui.
Mas eu tranquilo. Se todo mundo coisa só. Pode ter depois, eu acho que vai interromper mesmo. Talvez interrompa lá automático. Porque lá no OBS. Primeiro o YouTube, resolve o YouTube, depois interrompe lá no OBS.
Beleza. Interrompe a transmissão. Ok.
Mas o mais importante é o YouTube e os estúdios, né?
Beleza.
Esse aqui é o que está transmitindo para o YouTube. Mas esse aqui, talvez ele interrompa automaticamente. Mas não custa.
Tranquilo.
Rola uma dessa.
And all of my first and all the properties of the Boltzmann and now finding this one particle from particle information probability between. That contains now all the information that you need to write down given Boltzmann. And we have some simple models where they tend to be now you can do it if they're flesh out and we love to see. I need to learn not to see more time. And just a brief little thing because I was here last time visiting our Carlos, and I always thought this should be obligado because it goes for applied English, right? And when during the conference there, I actually thought everybody write with at the end of the slides. Yeah, so that's the different thing to see how. And with that, I thank you for your attention. I'll save my time here. Thank you.
Yes. So I'm sure that your question allows you.
Yeah, so I've been doing this since my PhD days. So I started my physics degree Germany in field health. They did a master's degree on chaos semiconductors. But it was just this model of a single order integration equation. And then when I examined it as a PhD student at Oxford University, basically for the record before as an exchange student, so they knew me. So the way it works is you're going to pick an advisor out of everybody who's there, and they gave a brief introduction to what they were doing, and during the year, time was telling me about this, was telling me about the work she was doing, which was very early then Boltzmann mechanics, so multifásicos, very complex phenomena. It's always been complex phenomena that was very interesting as a student. And so I thought, well, this would be a good way to go. Actually, while I was a student, she got some extra funding to do research in this very particle that I'm asking you about research to get more money there. But I like these methods, and I think quite happy when they say this. It's very important methods that, and I would agree, there's a lot of fundamental stuff, some of which I'm going to talk about here. There is this basic simplicity of the method. The method itself is trivial. If you write it down, it's so easy to do. Right? You don't know each robot Navier-Stokes, you don't even know what differential equation. It's only when you're trying to understand why this method actually works that it becomes complex. But this fundamental simplicity of it is always really striking. Well, you have to, I told you this, that again, always ridiculously simple, right? And you can solve things like shock waves with it, which is kind of exciting.
Thank you. So we have time for questions.
Don't be shy. Yes.
Okay, I have one. So first of all, thank you for lecturing, and I have a question regarding the part where you mentioned the cell-based and the course, right? So basically, we know that Lattice Boltzmann is a time-based method. So in that point, do you use something like to evaluate the cell-based method? What do you do? You keep like doing this point-based, or you continue to do something related to cell-based?
So what we do is this. So you have so the Lattice Boltzmann mesh is the blue mesh. Particles sitting on points, moving from there to there in points. What you do is we interpret it that this point actually corresponds to a whole volume around that point. Right? So all particles that are in this red box around this center point, those are the particles that belong to that cell. And then obviously they belong to the other cell. Right? So this is how the way you move from one cell to the other is really the move from here. Right? Which raises all kind of questions. It's all dirty in your head. Because if you move from here to here, you move a large distance. Rather than moving from here to here, it's moving behind distance. And that looks like it's something very different, right? And there should be differences coming out, and thanks to that gas around the box, if every day, it should not become all right. Yeah.
Right.
Yeah. That was a very good question. Yes. So that's a very nice question. And I'm just telling you what we're planning when we have not actually implemented this. But the idea is exactly the same as here. But we have two different canvas pieces, right? But then they're in the same box, right? But now we have then the A part and the B part, we have two separate Boltzmann equations, two different Boltzmann equations. And this left one, and then the green particle the network. But if you get here, and then you have exactly the same magnetic flow as we have here. But you would count having the one species to one of the manifold converts and the other to the manifold convert.
It's still to be done, right?
This is still to be done, right? There's some work that I put there in the image. I guess the mapping between the integration and organic integration. I'm not sure about the same. If you're trying to map them onto each other, it's not so obvious, right? I mean, the way you arrive at this extended interface, right? That allows you to make data expansion way they always know the super term that you can put in and the physics in the model. The edge may not look quite like this. Right? Or at least we don't quite know how they map onto each other, right? So does this learn-out interface really correspond to the certain extension that we get in the interface models? I really don't know.
That will give you the connection between the top down and bottom up.
Exactly. That's what we would like to understand.
So it's actually
Maybe you'll find it like that wrong. I mean, we just don't know. That's what we know about that.
there's still time for one question. That's one. Yes. Yeah. So
First question, two questions.
yeah.
Right. So, this work is academic work. However, in developing these methods that are being used for many applications, like the petrograph also, but many other applications as well. So, it's like deriving, deriving things like the Navier-Stokes equation from first principles, right? And it's actually not as well understood what the correct body phase equations ought to be, right? And if it puts them on a more fundamental basis, that if they look exactly the same as what we're using right now, then we could have just derived what we already know. But if they look different, we might actually have better equations that might be better equipped to solve some of these body phase problems. And then they would become really practical, because it would look different, right? If we just derived what's existing, that would give us confidence that what we're doing all along is good, which is fine. If it looks very different, then you would have something that might actually be much more useful. But we don't know which one it's going to be yet.
We can see the again becoming already. What's your thought? Exist to in the major assumption is the box failure on the room.
Yeah, so that's an interesting question. So the number of so the question is, if you have a flow that's very fast, right? So there's a sound speed that comes out of the temperature that's involved in here, one of us going extreme. That's also the speed that the sound wave will move. Except, of course, these models are isothermal, right? They feel sound waves there, so you want to have an energy equation in there. The other thing is you don't want to, if you move, well, these models, there's this kind of velocity that can move, the most one cell per time, right? This is as far as people can't go any further now. These ND models, of course, they don't care, right? You can have photonic, will particular weird stuff like that, right? So you can use this mapping, and I think it's not done, but we think about it. I think what's going to happen if they're moving very fast. This is not going to be velocity, they'll actually move further, right? And you'll have to probably make a velocity that local that depends on the local velocity. But formally, the way this comes out is that the packet allows all possible velocities, right? And all possible displacement, and then the Gaussian, while the likelihood of this moving forward is 10 to minus 24. So it's not zero, but it's there in principle. So the MDLT mesh contains all possible displacements. And you have to do some kind of pruning probably for quantitative application. So you look at only ones that there's too many secrets. I mean, within your simulation, you find at least one part excluded there, right? Because at this time, that you'll find no part of thing for. If you run this to life, the universe is never going to happen. It's not. There will always, it's close enough to zero, that essentially there is the practical and formal simulation probably going through your velocity set, but that velocity set will now move this is through. And you will also get, you can still be this kind of velocity set, but now it will depend where you are looking over velocities, how they will move on. And that's a really interesting application. I don't know, now to do it. Don't think that hard to do. Because relatively straightforward, we do this in your simulation. And then you can see what are the consequences to that on the back. What are the resulting that Boltzmann method look like? I think that's a very, very nice question.
Okay, with that question, we close this session and we're going to thank Professor Alex for the